Hi, how's everyone doing? I'm audible.
Yeah, doing well.
Thank you. So again, waiting for a little while, letting everyone join. So for today's session, I have created a new folder, week 2 office hours. I just put the link in the chat, so maybe everyone can quickly open this link in Google Colab. Okay, so I think we are 10 right now, but let's start because we have to cover a few things. So, what we are going to do is essentially try to finish the work that we were supposed to finish on Friday. So, there were, I believe, two cells for which we still had to write code. So, we'll be doing that today. Before that, I want to take a little bit of time and just explain because we are midway through the course. So, I want to explain what we have covered so far and what we will be covering in the next 2 weeks in terms of the syllabus. So, I'll very quickly present a few slides, and after that we'll go back to writing code. And once again, the link to today's notebook is in the chat, so please open this in Colab. It's largely the same code that we used on Friday, but I just removed a lot of fluff because it was a long notebook, and I added a few cells at the bottom to give you a glimpse of what is in store um, for the next week, or at least the next session. And the link is in the chat, so you can open it while I go through the slides. So this is the course syllabus, right? We started with the foosball project. We have been trying to solve it. We attempted to solve it with dynamic programming, uh, which was an easier version where we used an internal API. We had access to the states and their transitions, and we used that to build a dynamic programming solution. But then next we talked about a more realistic scenario where you don't have access to the states, you don't in advance know about what states are there and what their transitions look like and what will be the rewards corresponding to those transitions. So we sort of attempted to solve that in the last session. And in the next coming week, we will be looking at improving the solution, because as we'll see today, the solution that we attempt today does not fully solve the problem. So it doesn't give you a policy which is as good as the one you got from dynamic programming, but it is our first attempt, and then we'll make incremental improvements in the next session. So in terms of what we covered so far, the first thing that we have been talking about since the start of the course is why reinforcement learning is needed at all. And I said that we don't want to discuss everything in the beginning. We'll keep coming back to this. So I think now is the right time to start thinking about it. So in how why reinforcement learning is different is because when we are doing supervised learning, we try to learn something from examples. So each data point is accompanied by some sort of a label or labels, And then when we are learning, when we have learned from that data, we want to predict those labels correctly. So that is learning by example. In terms of planning and control problems, we essentially want to learn from experience. And the reason we want to do that is that, uh, first of all, planning and control problems are more complex in general, but there is also a big cost to labeling the data, right? And for problems that are typically solved using supervised learning, you have to deal with that cost. For planning and control problems, it may not be feasible to do that, because there are a lot of states and actions. You can imagine that even if you are willing to pay, there are so many different combinations that someone will have to spend a long time and a lot of money to get everything labeled, all possibilities labeled. So we want to automatically learn from experience the way humans do, without actually having to label everything. Uh, and Of course, that is why the labels typically in planning and control problems are sparse, right? So if you are trying to train a car to drive around a track, then you will have rewards. That is something that we as engineers, we will come up with some sort of a reward signal, but most of the time the reward signal will be empty. um, or at least the goal will not be to minimize the reward signal. The difference between the actual reward and the reward that our algorithm gets, the goal is not to minimize it at every step. The goal is to maximize the overall accumulated reward over some time horizon. And the fourth thing is the data set. So when we are doing supervised learning, be it NLP or computer vision, so you typically you try to solve a problem and you get a data set which is representative of the data that you will get when you deploy your solution. So if you are predicting labels for images, then you have to get a data set which is representative of all the possible variations that your algorithm will see. In the case of planning and control problem, the data set is not static. It is generated by your algorithm, because the algorithm controls the agent interacts with the environment. And so this is what you want to do is you want to get data from the environment, you want to get good data from the environment, and then you want to train on that data. So it's actually a twofold problem. So as you go along, you generate data, then you train on that data, and if things have been fine tuned correctly, then you generate good data, and from that data the behavior you learn, that improves over time. uh, but can supervised learning at all be used for control and planning problems? This is what we asked in the context of driving a car. Is it possible to just take, for example, camera images of a car, of the road ahead of a car, and predict from that the steering angle and the throttle and the brakes and everything? So it seems possible. There has been some work. There are a couple of links included in the slides. You can do that, at least for short horizons. For example, in this case where you want to look at the road and perhaps guess the curvature of the road, and then also try to estimate the correct steering angle, then that seems doable. There have been research papers published on that. But then there are a lot of other tasks where you really want to focus on a very long term task, with no immediate there's nothing immediate that you want to achieve, but you want to achieve a long term goal. And for them, supervised learning don't seem to fit the bill. Right. So, what how we got started? We looked at control problems. The first one was the car problem. Then we looked at a more simple one, which was fool's ball, because the car problem had continuous variables, like the steering angle and speed and everything. They were continuous. So we thought we'll do something which is in the discrete space. So we picked up fool's ball, and we modeled the whole problem in terms of an environment and an agent that is interacting with the environment. This is the diagram that you'll see everywhere. So the agent interacts through some action, and then the environment, changes its state. It's actually the agent and the environment. The state is a description of the agent and the environment. So the state changes, and then there is some reward. Reward could be sparse. You could get something at every step, or you could get something only at the end of a number of steps. So and then what you want to do is you want to learn that sequence of best actions so that the cumulative reward is highest. So maybe you are losing out on the immediate reward a little bit, and if you plan it correctly, in the end you get the highest return, the discounted reward that we have seen, right? And what this essentially translates in terms of code is that you have a table, you want to fill up this table. So corresponding to every control problem, you have states and you have actions. So you want to fill up a table which has dimensions n states, number of states into number of actions. That was our rewards table, and we want to fill up every entry in that table with the best reward, the best return you could get for that combination of state and action, right? And this is what we want to solve programmatically. Now, how do we solve it? We saw that it's best to define the return for the terminal states to be zero, because you just can't take any actions in the any of the terminal states. So you define them to be zero, and then you use the recursive property, because the problem is modeled in terms of state transition. The states are naturally recursively, the the the, the return for the states is naturally related to the next state, right? So the return you get for state t by taking action t at time step t, that is naturally related to the return, the best return you can get in state t plus 1 for different actions that you could take in state t plus 1. And in this case, where you have exactly 4 actions, this was the recursive relationship. And we tried to solve it first with dynamic programming, different variants. So we tried dynamic programming, but then we saw that this is not your typical dynamic programming problem, because there can be indefinite recursion, because you can go back to one of the states, and that creates a cycle. So if you're there is no natural termination point. So what we did was we tried something, some sort of a trick where we filled up the table in the beginning. So we took arbitrary values. We just we filled up everything with zeros. It could have been any random number as well, but we filled it with arbitrary values, and then we applied the same recursive equation. But instead of function calls, we just looked up the table, because those entries are already in the table, so there's no need for recursion. uh, Now we applied the recursive equation to every entry in the table, and you go through the entire table, scanning every cell and applying this equation. But that is just one iteration. To actually get to a point where you have the returns in the table are actually good returns, they are representative of the actual returns, that the best returns you can get, you have to do it over and over again. So that is what you do through, you write another loop at the top level, which repeats this process of updating each cell in the table. And you just run that loop, until there is convergence, or until the values in the table stop updating, or they're updating by only a small amount. So this is the code. This was there in the notebook, and this was our approach. uh, this is what we tried for convergence. So we just wrote a loop at the top which ran for 50 iterations maximum, and we kept checking if the delta, the update was small enough, and then we broke out of the loop. And this indeed gave us a good result in just 9 iterations for this case of foosball. Uh, so once you fill up the table with the best returns you could get for every state and action, the next step is really very simple, which is picking the best action, the action with the best return for every state. So you just scan the table top to bottom. You start with your initial state, then you pick the best action, and then you see which next state you would be in once you take that action. Then for that state you pick the best action, and this gives you a sequence of state and best action pairs. which we call the policy, which is the solution we were after. So that is actually called an optimum policy, but it's very simple. Once you have the returns table filled up correctly, then it is just one pass through that table and you have your policy. Okay, but then we started exploring a more realistic problem, because earlier when we were using the dynamic programming approach, the iterative one, we were sort of peeking inside what is going on in the environment, which is looking at what transitions are possible and what rewards correspond to those transitions. But in a more real world setup, you won't have access to that. So if you start solving, trying to learn to drive or learn to play a game, you won't know what states are possible, what are the different things that can happen in that game, or in the case of driving, what are the different possibilities in which the car could end. So you don't have access to that. So we still want to solve the same problem. We have a table, returns table, that we want to fill up, but now you cannot directly look up the reward for every state, every state next state pair. And that is where the learning from experience part comes. So because our knowledge of the environment is incomplete, we don't know which states are there, don't know what transitions there are and what rewards correspond to those transitions. uh, the simple thing is that we will try to get to know those things by just interacting with the environment. And really the simplest approach is just taking random actions, because you don't know anything about driving, or you don't know anything about the game of foosball. So you just, in the beginning, you'll try random things, you will fail sometime, you will make some progress sometimes. But every time you try a sequence of steps until that game ends or the car crashes, and the experience you collect, that is called an episode. So from that experience we can, uh, you know we all along with that experience, we get the state transition, we get the reward for every state transition. And that is all the information that we need, because if you have a sequence of state action, next action, pairs, then and you also have the reward for every transition, then you can essentially compute the return for every state and action pair, right? So what we did on Friday was basically we created random episodes. So start in the initial state, reset the game, start in initial state, then act randomly, then you will go to some other state, keep acting randomly and collecting rewards. And then from the rewards we computed the returns, the discounted returns, and we tried to fill up the returns table again. The problem is that when you just when you simulate a few episodes, the returns that you get are not representative of the best returns that you could get, because we are just randomly acting, right? So maybe I was in front of a defender, and the random action was to try to just move in the direction of the defender, which is not the wisest thing to do. But that is how we are collecting episodes. So what we need to do is collect a lot more episodes, and then if you average over those episodes, there will be instances where you took a bad decision, there will be instances where you took a good decision. So it will at least average out. And that is what some of that we are going to do today, and then some of it we'll do in next session. So we'll see how, instead of taking just random decisions, if we can take more informed decisions. We still The process is still the same. You generate an episode, and from that episode, you have the returns, and you have the rewards, and you get the compute the returns, and then you try to fill up the table with those returns. What we are going to look at today is, instead of just taking random actions, because you are already filling up the table, so you already sort of know which actions are the preferred one, which actions get you the best returns. So why don't we consult that table and then pick the best action for any state, instead of just selecting a random action. And this is roughly what we will do today and in the next session. So we will what we'll do is, let's say at any time you have some entries in the table, so generate a few episodes using those entries, right? So this time use the table to generate episodes instead of taking random actions. And then once you have a few episodes, use those episodes to estimate better values for the returns in the table, and do this over and over again. So this is roughly what we will be doing actually in the rest of the course as well. So we'll make incremental improvements, but the overall strategy is going to be same, that you consult the table, you generate episode from it, several episodes, and then you average the returns over those episodes for every state and action pair, and then you again go back and update the table a little bit. Yep. So just a few things that we'll do in the session on Thursday. And then in the next session on Friday we'll put everything together. So all the different approaches, the vocabulary, the terminology that we have been using, and there are things that we haven't specifically named so far. So we will put together everything. uh, what we the problems we have been solving, they are called Markov decision processes. So we'll talk about that. And then the tables we have been building, they are action value tables, the returns table that we have been filling. So we'll give everything a name, and then different types of policies, and the approach that we're taking right now, which is generating episodes and learning from episodes. That also has a name. So we'll talk about that a little bit. uh, and then the naive approach where we were just using random actions, and the other approach where you are consulting the table, returns table. They are called exploration and exploitation, so we will give them those names. And then we'll specifically talk about a few algorithms. There's something called q learning, and there's something called sarsa, which is like we will have a good grasp of how they work. But in the session 2 we'll give them these exact names, and also look at the mathematical formulas that we would already have implemented by that time, but we will look at the underlying mathematics. And then of course we'll start talking about the project for this first course, which is the OpenAI gym problem. Should be really straightforward to solve because we would have done a lot of experimentation with our own environment. So we should be set up to quite easily solve this problem. And at this point, if you feel that this is a very easy problem, you want to aim a little higher, maybe solve a more complex problem. So that is also a possibility. Yeah. And then in week 4 we will do something very important, which is introducing stochasticity. So far, whenever you take an action, uh, the next state is fixed. Once you know this current state, and once you fix the action you are going to take, the next state is fixed. That is not at all realistic. There is probability at play, whether you are driving or playing a game. There is always a chance that things will not go exactly as you plan them. So if you want to go forward, there is a small probability that you will actually go down, or go diagonal perhaps. So we will include that into our own environment, and we'll see how to modify all the equation, all the work we have done so far, for cases where stochasticity is present. And then we will also embed a little bit of AI in our existing agents. So we will maybe implement simple AI algorithms, so that our defendants are actually tracking the ball, they're trying to block the agent, and then we'll see how the agent can still learn a good policy in the presence of this behavior. And then we'll take look at a glimpse of some of the other problems, like the car driving problem. We'll go back to that, where you have continuous state and continuous action, and we will see how to either convert them into discrete space and discrete action problems, or what other ways are out there to deal with such problems. So this is everything we are going to do in this course. Now, I would like to go back to the code. I hope everyone has opened the new notebook. I'm sharing the link once again. Like I said, most of the cells here are from last week's notebook, but I have removed a good chunk which was not at all necessary for what we are doing right now. So there were a lot of cells where we were experimenting with the environment, for example. I've removed that. So try to open this notebook. I'll also run all the cells, all the work that we did up till Friday. Right. So we did all of this. We wrote this function to that filled up the returns table, and then we also wrote this piece of code which basically ran the function until there was convergence. This is the result we got. Then we defined a policy, and we also plotted the policy, and we sort of solved this initial problem, right? This policy, no matter which state you were in, this policy gave you the best sequence of actions which will have led you to the goal state. And then we started thinking of the more realistic version, where we started by collecting a random episode, and now of course this is going to look different every time you run it. So this time I have got a very lengthy episode, but the length will vary. uh, but then we saw that if you have episode, then we implemented this method which just took an episode, and it calculated the discounted return for every state action pair. So if the episode has a length of 3, then which means if you remove the terminal state, then there are 3 states, s1, s2, and s3. Then it will compute the return starting in this state, the return starting in this state, and the return starting in this state. And we saw a typical output. The next thing, of course, what I was talking about a while back, is now we need to do a lot more episodes. So one episode is not good enough. From one episode, you will, of course, be able to calculate the returns for many different state action pairs. But one episode will likely not cover all the states. And even if it covers even state and action pairs that are part of an episode, uh, the return that you get from just one episode is not going to be representative of the best return you can get. So you need to do uh, a lot more episodes. So generate maybe 100, 500, 200 episodes, and then uh, take the average return. So now, instead of having, if you're looking at this code, the we have two tables now. One is the estimated returns table. Of course, these are estimates because these just depend on how many episodes we want to simulate. And then we have the visit count as well. So both have the same shape. I mean, number of states in rows, the number of column, and number of actions in the columns. And what we want to do is we want to, whenever we encounter a specific state and action pair, we want to just accumulate the return corresponding to that state action pair. in this table, the first table. And then we also want to keep track of how many times that state action pair was visited, because it's likely that during one episode, or when you're doing multiple episodes, then it's likely that uh, you will pass through the same state action pair more than once, and you will likely get different returns. So we want to accumulate all the returns, and then we divide by the number of visits, and that gives you an averaged out version of the return, which is better than relying on a single episode, a single visit to a state action pair. So that is what we want to finish today, because then we will look at improving things. We'll see that once you write this code, we'll be able to get close to the best solution, the best policy that you can get, but we won't exactly find the correct policy like we did with dynamic programming when we had access to the internal state transitions. So I would like everyone to again go to the breakout rooms and give this a try. Remember, there are two tables. We already have the method, we have the function to generate the discounted returns for entire episode. So all we need to do is, if number of episodes here is set to 100, then we need to generate 100 episodes. For every episode, generate the return for every state within the state and action pair within the episode, and then just accumulate those returns in this table and keep track of the visit count in this table. So I'm going to open up the breakout rooms. Let's take 5 to 10 minutes to attempt to write this code.
Hi, Farhan.
Hi.
I got a chance to like go through the parts and try during the weekend as well. But one question I had was, in this box, the one that you're showing right now, and the second one, estimated returns is equal to the returns table divided by the visits counts table plus one, right?
Yeah.
And I see that plus one is to make sure that the states that we don't enter into, like they're going to be set to zero. So you want to increment it by one. But for the ones that you visited, aren't you adding another one to it?
Yeah. That's right. So it's not going to be as accurate, but if the number of episodes is large enough, and then it will have a small influence. This, instead of making it once, we could have added a smaller constant. So
Mhm.
if you think,
But if you were like visiting only like one time, for example, you're just
yeah,
dividing that by two then, right?
right.
Which would
So
be inaccurate.
which will be a large error. But if you are visiting 10 times, then it's probably not that large. So instead of adding one, we could add a smaller constant, which is typically what is done, right? Like 10 to
I
power
see.
minus
Okay.
3 or something.
Yeah. Okay. And I see that no matter how many, like I tried 2000 for number of episodes here as well, but it never really reaches that good accuracy. It only really follows the same path, and I see that there's arrows that kind of point in different
Yeah,
direction. Or if it doesn't visit at all, it just goes to the first state, which is north, right? So it just points north all the time. Um,
so it won't improve a lot, because we are making random choices, right? We keep taking random actions. So
mhm.
think of any learning problem. If you are just trying random actions, it's not going to help. What we
Yeah,
usually do is that if I'm learning to play a new video game, for example, I'll in the beginning perhaps take random actions, but just after a while I will find bits of information, and then I'll improve my actions. I'll know
mhm.
which controllers control which parts of the game, which directions to go, whatever information that is. But I'll very quickly improve those actions. I won't keep them totally random. That is what we are going to do in the next step.
I see. Okay, thank you.
Sure.
I can't hear you at all. I don't know if I'm the only one.
No, you're right. I was muted. Sorry about that. So I was saying that this is the solution, and what we're essentially doing is generating an episode, a random episode, and then we are feeding that episode to this function that we wrote earlier, right? So this function will take the episode. The hyperparameter is same point 0.9, and it gives you the states, the actions, and the discounted returns. And the discounted returns is going to be a list because you will have discounted returns for every state action pair in the entire episode. uh, then what we need to do is, so you have state, action, and discounted return, and we are interested in the discounted return part, right? So we just loop over this thing, loop over state, action, and discounted returns, and we just accumulate the return. So you go to the uh, row corresponding to the state and the column corresponding to the action, and you accumulate the return there. And then we also increment the visit count by 1. This is all that needs to be done here. And with this, and the number of episodes set to 100, and if you look at the code in the next cell, then you are essentially dividing this table by this other table plus 1, because we don't want to divide by 0 anywhere. If some state has not been visited at all, we don't want a division by 0. This will skew the value a little bit, because if the visit count is really small, then if you add plus 1 to it, then the denominator will change significantly. But for our purpose, seems to be working. So let's try to divide this, right? And try to print the policy, right? uh, I think everyone should get something similar. It won't be uh, I think someone ran the code for 20,000 steps, and then the policy they got was essentially the policy that you determined from dynamic programming, which is the best policy for every starting position. But what we get here in just 100 steps is a policy which is somewhat okay. It has a few arrows that are pointing in the right direction. If, for example, if you start over here at the bottom, then it tells you to go up and right. And there are things that look okay. It tells you to go down from here, but then it gets lost somewhere. uh, you know After a while, it will point you in the wrong direction, and there are loops and stuff. So this is far from perfect. One thing you could do is try running this for longer number of iterations, 100, 500,000, and that will improve things. uh, but there is a fundamental flaw with this approach, which is that we are taking random actions all the time. So if you think about it, we are filling up the table, and the reason we are filling up the table is because we want to find the best policy, and policy is essentially your guideline, right? That tells the agent which action to take in which state. So then why are we taking random actions all the time? It makes sense to take random actions in the beginning, when you don't know anything about the environment. You just want to, what is called, exploring the environment. So you want to explore the environment, so you just try random things. If I'm learning to drive, perhaps in a video game, at least I'll try random things in the beginning. If I'm trying to learn this game of foosball, I'll probably try random things in the beginning. But very quickly, after just a few iterations, I will have a specific pieces of information, and then I will change my actions accordingly. So if I get to know that there is a defender somewhere, because I just lose the game every time I go into that cell, then I'll try to stay clear of that cell. And we are not doing any of that here with the random action. So we keep repeating the same mistakes over and over again. And really, what we want to do as the next step is make use of that information, right? So if you look at step 12, it says exploiting the information in the returns table. What is the information there? It has, it has a return associated with every action for every state. So it is exactly telling you what you need, which is what is the best action to take in every state, right? So why don't we make use of that information? Now we are almost over time, so I don't want to like try this right now, and this is anyway meant for the next session. But the idea is that instead of calling this function, this function collect random episode, let's create a function that generates an episode from a table. And how do you do that? We have done this in the past as well when we wanted to print the policy corresponding to a table. So just start and like reset the game, and then use the table to find the best action for every state starting in the initial state, and collect an episode which we will call a greedy episode. Greedy because you are taking the best action, the action with the highest return at every step. So use that approach. This line will change essentially. And so first of all, you need to implement this function over here that gives you a greedy episode. Sometimes we want to cap the length of an episode because um, you know in a situation where the game may not terminate, you don't want to create a very lengthy episode where perhaps you are caught in a loop. So you want to cap the maximum length. And but yeah, essentially you need to look at the table and generate steps from there. So starting state, best action, then you get to next state and best action, select an episode. The rest of the code is going to look more or less the same. That will be implemented in step 13, which we'll do next on Thursday. But this should improve things for us, and then we'll see that even this approach is not 100% perfect because uh, first of all, you don't know when to switch from the first strategy to the second strategy, right? In the beginning, you definitely want to try random things. You don't want to look at the table because the table is just very inaccurate in the beginning. So that is one thing. So what you want to do is you want to sort of find a point where you want to transition from random to tabular approach, and then even when your table is filled up with more accurate values, say after 100 iterations, you don't want to entirely give up on exploration because because we know that the table won't be perfect until you have found, until you have found the solution, until you have a perfect policy in place. So you cannot 100% rely on the table all the time. So you need to, occasionally you need to carry out a random action instead of consulting the table. So in step 14, we will sort of blend the two approaches, and we will make it a smooth transition where you start with a totally random approach in the beginning, but then slowly over time, you have this blended version where most of the time you're looking up the table to consult the best action, but occasionally you are also taking a random action. If you look at, if you have been through the book, through the chapters, or looked at any of the resources, then they call this the exploitation dilemma. So basically, like humans, the algorithm has to decide whether it wants to put more focus on exploration, which is trying out random things, or exploitation, which is consulting the table. And then you have to strike a balance between the two to get a good policy quickly. So we'll look at that in step 14 on Thursday. And after that, basically, once you implement this exploration exploitation, then you should be able to get to a solution much more quickly, and a policy that gives you the right steps no matter in which state you start. So we will see that. And after that, in the next session, like I said, we will talk about two specific algorithms which are called Q learning and SATSA. So we sort of would have implemented those algorithms in terms of code, but we will see how, like, what they look like in terms of the mathematical equations and how to map those equations to the code that we have written. And that will sort of cover everything that we needed in terms of basics, because this first course was meant to be an introduction. So you will have everything that you need to then get started with uh, employing deep learning algorithms in course 2. But then in in uh, in l- in the last week we'll do one thing, which is introducing stochasticity, which is also important. So that will add the last bit of realism to our environment. actions won't be 100% accurate, and we will see that we can modify this approach. So you just have to, so because whenever you take an action now, instead of having you know, in next state you will have a distribution of states, because it's possible that you can end up in many different states, and there will be associated probabilities, so you have a distribution of states. And we'll just see how to deal with that, and those like a few small changes, and you can adapt these algorithms to those use cases where there is uncertainty. And after that, we will also talk about the project that we have to do for this course, which should be fairly easy. So I'll wrap up today's session. If there are questions, please ask now. Otherwise, you can ask them on Slack. Um but yeah, on Thursday we will start from here.
I noticed that in the collect random episode, you always start from the initial state. Would it make sense to also randomize that state in the collect random episode?
Yeah. So that sort of depends on what you want to achieve, because we were saying that we always spawn the player in the top left, so we are starting there. Otherwise, it would make sense to start from random positions.
But you're trying to build a table with everything. Like I noticed that a lot of the table is very sparse for states that are unlikely to reach if you start from the top. So even
Right.
though the rule is to start from the top, I mean, would it make sense to randomize the start point so that you get more coverage in the table?
Yeah, we can try that. But then you have to modify the environment, right? Because right now we don't have an API to start in a random position, right? Because when you reset, you are basically going to 0 comma 0.
So
So
you
you
can't
will,
just do state equals reset and then state equals NP random choice among the states.
you can do that. You can do that. That will be a little bit of a hack. You can change the state externally, but if you want to do it in the correct way, then perhaps there should be an API to do that. Make sense?
So one thing that I noticed is even if I pick 20K iterations, it
Yeah.
still doesn't converge to the one that um, provided by the dynamic solution. I think few other folks in the same
Right.
breakout room is
And we
seeing the
don't.
same.
I think we shouldn't be expecting. I mean, I think someone said that they got the policy right with 20,000 iterations. Uh, but I won't expect it to converge, because, like I said, we are trying random things. So with random things, there is a limit to how much you can learn by just trying random things all the time. So until you implement step 12 and then step 13, I won't expect to get a policy at with even 10,000 steps.
So it sounds like with random choice, even with very large iteration, it may still not converge to a good solution. Is that uh, what's happening here?
Yeah, that is right, because we are generating random episodes, right? So uh, we keep on learning about the environment, but we are setting aside all that information. We always try random things, right? So depending on how large the environment is, you might be able to just keep doing this and learn everything after a while, say 20,000, 50,000 steps. But in general, it is not the most efficient way to learn a policy.
Okay, thanks.
Cool. So, where the notebook is, there is there is no homework as such until Thursday, but we will have a few readings. Like after we finish probably session one on Thursday, we will have a few readings from the resources I shared earlier. And if you get time, then yeah, please try to implement the other functions. Otherwise, we'll definitely do it in the classroom. Just at least look at what we are going to implement on Thursday. Cool. I think then let's wrap up. If there are any questions, I'm going to upload the recording. It does take a while before it gets available. So I'll share the recording as well. You know where the notebook is. Uh, so yeah, let's meet on Thursday then.
Thanks for all.
Thank you. Bye bye.